Good afternoon, everyone. So, we'll wait for 5 more minutes for others to join. If not, we'll start the session by 3:05. Thank you. So, instead of just waiting for the time being, I would like to give you an idea about the course if you are new to the course. So, this course is Fluidization Engineering, and I hope you all know about fluidized bits as of now because already we are into week 7 of the course. So, what are fluidized beds? Can anyone say that? Okay, fluidized beds are uh, setups which we use in industries because they have efficient heat transfer and mass transfer. Why is that? Because in fluidized beds, we pass the fluid inside the packed bed at a very high velocity, or we can say sufficiently higher velocity. In that case, the particle starts to move, and when these particles move, they behave as fluid. That's why we call them as fluidized beds. And because they have started to move, the contact area between the fluid and solid has increased, and which in turn increases the heat and mass transfer coefficient, I mean mass transfer rates, depending on the condition which we require in the system. So that is what fluidized beds are. So this course, Fluidization Engineering, is all about fluidized beds and various things we deal in fluidized beds. So myself, Ankara Kartika from IIT Hyderabad, research scholar from the Department of Chemical Engineering. So the course is NPTEL course, and the course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. So these problem solving sessions have been happening every Friday, Saturdays from 3 p.m. to some 5 p.m. So already we are into week 7. We have almost covered half of the course. So just to give you an idea on course layout, because the time is not there, time is not at 3:5, so we'll just see what we have seen till now. So we have seen the introduction to fluidization and advantages and disadvantages of fluidized beds, industrial applications of fluidized beds. So I mentioned about the advantages of fluidized beds. Does that mean fluidized beds does not have any disadvantages? No, it doesn't uh, happen like that, because since the solid particles are moving and they can cause erosion of the particles, and if we are using valuable materials, the probability or the possibility for these particles to get broken down and getting loss of the materials is also there. So there are certain disadvantages as well, but depending on the applications we need to identify whether we require fluidized beds or not. Also the pumping cost is higher over here in fluidized beds. So what are all the applications of fluidized beds? Fluidized beds are used in various industries. FCC catalysis process involves fluidization, and if you think about unit operations, mixing, segregations, and coating of some material over the solids also involves fluidization. So all these things and various reactions in terms of catalysts involve fluidized beds. So fluidized beds are widely used in industries as well. And later on we saw the classification of solids, because we have seen that GELDAT classified the solids into four categories: A, B, C, and D, depending on their size and relative density between the fluid and the particles. So each class of particles behave differently inside the fluidized beds. Those things also we have seen. And finally, flow characteristics, like inside the fluidized beds, it hydrodynamics doesn't remain the same always, depending on the fluid velocity through which it is passed, and the fluid like fluid type, whether it is liquid or gas. All these things influences the behavior of the fluidized beds. And later we also saw about the flow pattern inside the fluidization, like from packed bed and minimum fluidization condition, minimum fluidized bed fluidization, and fluidized beds, bubbling fluidized beds, or smooth fluidization when we use liquids, uh, and like in bubbling fluidized beds, after which we have seen about slugging, turbulent regimes, everything. So all these things, flow pattern and flow pattern map, and frictional pressure drop and its models to analyze. So also we have seen about the frictional pressure drop, and how pressure drop is important in fluidized beds and how it is influencing the uh, cost of running the applications is also studied. And solid movements, mixing, segregation, and staging, all these things also we have seen. And week 6 it is about gas distribution system and types of gas distributors in and small and large scale industries, and design of distributors. Like we have seen about porous plate distributors, perforated plate distributors, nozzle tube type distributors, bubble cap distributors. So all these things we have seen. And later we are starting with bubbling fluidized beds. Last week it was an introduction to bubbling fluidized beds. Okay, solid movement, mixing, segregation, I think it comes in later stage. We haven't yet covered in terms of problems. And so last week 6 we dealt about bubbling fluidized beds, gas dispersion. And again in week 7 we are going to study some more about bubbling fluidized beds and cover everything. Later on we'll see about the entrainment and filtration from fluidized beds and attrition. These are the mechanisms by which I was telling about the loss of the solids inside the fluidized beds. And later it is about mass transfer phenomena, particle to gas mass transfer, and its model analysis in 2 and 3 phase systems, and heat transfer phenomena at last. Design of fluidized bed reactors. So that is the thing. So now we'll go to the problems. Okay, as far the books are concerned, the first book is Fluidization Engineering by Coney and Levenspiel. This is a must read if you want to master the basics of fluidization. And next one is Giraspo's Multiphase Flow and Fluidization. Third one is Givlaro's Fluidization Dynamics. And fourth is S.K. Majumdar's Hydrodynamics and Transport Processes of Inverse Bubbly Flow. So now we'll start with the problems similar to week 7 assignment problems. So based on these, it will be helpful for you to solve this week's assignment. I think submission deadline is Wednesday. Please check with that and submit the assignments promptly on time. So you'll get better score because as you all know, your final exam score also matters in addition to the assignment scores also matters in addition to the final exam scores, because the combination of the final exam and the assignment score only comes in your final grade or final mark whatever. So please be careful and submit all the assignments on time. And now the first question for week 7 is the coalescence of two bubbles in turbulent flow in a three phase two. The coalescence of two bubbles in a turbulent flow in a three-phase fluidized bed takes place due to. So this week's the problem is due to coalescence between the bubbles in the bubbling fluidized beds. So the coalescence can occur in two directions, in horizontal directions and in vertical directions as well. In vertical direction, it happens when the trailing bubble uh, or reaches the leading bubble and they coalesce, and in horizontal they move and they coalesce. So the weak assignments would mostly deal with the coalescence of bubbles, and it is mostly theory questions, so you must be attentive during the lecture which professor has given. So then if you are attentive enough, you can answer all the questions. So it is just a matter of time. And so the first question is about coalescence of two bubbles in a turbulent flow in a three-phase fluidized bed takes place due to. So why does coalescence takes place? Option A, bubbles collide. Option B, flattening of colliding bubble. Option C, trapping of liquid between bubbles. Option D, all of these. So I'll tell you that here it is given, it is a three-phase fluidized beds. Okay. So why does bubbles coalesce? So there are plenty of bubbles. We have seen that bubbles coalesce and they grow in size like that. So why does that happen? It happens when two bubbles collide, right? When two bubbles collide, what happens is that the surface of the colliding bubbles flatten, and then they trap liquid between the bubbles, and therefore they coalesce and they grow in size. So that is what we mean by coalescence of two bubbles in a turbulent flow in a three-phase fluidized bed takes place due to bubbles collide, flatten of colliding bubble, trapping of liquid between bubbles. So answer to this is all of these. Why? Because first they collide, and next the surface between the two colliding bubbles flatten, and they trap liquid between the bubbles. So the right answer is all of these. Option D is the right answer. Now I hope it is clear. Now we'll go to question 2. In question 2, it is given the collision of 3 or more bubbles at the same time has dash. Option A, very high probability. Option B, low probability. Option C, moderate probability. Option D, very low probability. So inside the fluidized bed, what are the chances that more than two bubbles collide, like three or more bubbles collide? The chances are very low, because like most cases if you consider, it is the collision between two bubbles at max. The rest of the things happening has a very low probability. Therefore the collision of three or more bubbles at the same time, we are talking about the condition at the same time. Just a minute. I think my Wi-Fi has gone. Please stay online. Okay. Power has gone over here. So I am connected from my Wi-Fi and my mobile data. Um, I hope it is okay. If there are any interruptions, please wait in line. So like I'll join back in 2-3 minutes. There is issues. That's why. Okay. Coming back to the question, the collision of two, three or more bubbles at the same time has very low probability. We are talking about at the same time, so answer is very low probability because at the same time the collision of three or more bubbles is not very feasible. So answer is very low probability. Option D is the right answer. So that is option D. Now let us move on to question 4. In question 4, it is given that according to the collision frequency model, the random motion of bubble depends on dash. Option A, bubble gas density. Option B, bubble frequency. Option C, diameter of bubble. Option D, bubble rise velocity. That is, in question 4, it is asked that according to the collision frequency model, the random motion of bubbles depends on dash. Option A, bubble gas density. Option B, bubble frequency. Option C, diameter of bubble. Option D, bubble rise velocity. So, in collision frequency model, on what basis the random motion of bubbles depends on? Answer is actually option C, diameter of the bubble. How, what is the equation? So the equation is this one, theta ij is equal to, that is the collision frequency, is equal to pi by 4 di plus dj the whole square ni nj into epsilon di power 1 by 3 into 1 plus di by dj to the power of minus 2 by 3 to the whole power of 1 by 2. Here I and j refers to bubble 1 and 2. So that is this. And now let us go to question 5. So I hope it is clear. According to collision frequency model, random motion of bubbles depends on dash. So the answer is diameter of bubble. So just keep in mind this statement that random motion of bubble depends on diameter of the bubble. So we will be having one more question in the same concept, and that time it will be very useful. So let us go to question 5. Question 5, it is asked that as per collision frequency, the buoyancy force between the larger bubble and smaller bubble has rise velocities ur2 and ur1 respectively. The relation between two bubble rise velocity is dash, where ur2 and ur1 are the large bubble and small bubble rise velocities respectively. So, as I mentioned, this one is similar to last question. So, as per collision frequency, the buoyancy force between large bubble and small bubble has rise velocities ur2 and ur1. So, larger bubble has rise velocity ur2 and smaller bubble has rise velocity ur1. So, what is the relation between ur2 and ur1? Without options itself, we should be able to say this. Can anyone say that? What is the relation between ur2 and ur1? ur2 is directly proportional, or ur2 is like greater than ur1, ur2 is less than ur1, whatever it is. Can anyone say the answer? Okay, and let us first look at the option. Option A, ur2 is greater than ur1. Option B, ur2 is less than ur1. Option C, UR2 is equal to UR1. Option D, UR2 is not equal to UR1. This one is okay. Okay. What is the condition? So, as we have seen that the motion of the bubble is directly proportional to the diameter of the bubble, right? So, if the larger bubble has larger diameter and therefore its rise velocity will also be larger. So, UR2 will be larger than UR1. Why? Because if you go and check the formula also, in accordance with the collision frequency model, you will be able to find that let us keep it UR is proportional to diameter of bubble. So UR2 is larger dia. UR2 is for large dia and UR1 is for small die. So therefore UR2 is greater than UR1. Answer is option A. UR2 is greater than UR1. UR2 is greater than UR1. Why? Because UR, that is rise velocity, is directly proportional to the diameter, and UR2 here is related to larger diameter, and UR1 is related to smaller diameter. Therefore, UR2 is greater than UR1. Hope it is clear. Now let us go on to question 6. In question 6, we are asked that according to Lair and Muse model, bubble coalescence occurs dash. According to Lair and Muse model, bubble coalescence occurs due to dash. Bubble coalescence occur dash. So Lair and Muse is a 2001 model for bubble coalescence study. And what is this? Option A, when a bubble enter another bubble wake. Option B, wave affect inline coalescence. Both A and B. Option D, none of the above. So according to Lair and Muse model, bubble coalescence occurs when a bubble enters the another bubble's wake. So wake is at the bottom of the bubble. So where some solids will be present. So when a bubble enters another bubble's wake, coalescence will occur, and also wake affects the inline coalescence. So both A and B are true. Therefore answer is option C. Both A and B is the right answer. Now let us go to question 7. In question 7, it is given that according to Hibiki and Ishii 2007, the coalescence efficiency results due to dash wake induced entrainment and turbulent induced entrainment. So according to Hibiki and Ishii 2000 model, the coalescence efficiency results due to dash wake induced entrainment, turbulent induced entrainment, both A and B. Option D only A. So answer is actually both A and B, because some models consider wake induced entrainment and some consider turbulent induced entrainment, but in according to Hibiki and Ishii 2007, the coalescence efficiency results due to both wake induced entrainment and turbulent induced entrainment. So both A and B is the right answer. Now let us go to question 8. Coalescence efficiency between two bubbles depends on dash. Interaction time, coalescence time, mixing time, either A or B. As you all know the answer, the coalescence efficiency between two bubbles depends on coalescence time and interaction time. So we say that coalescence occur when the interaction time is less than the coalescence time. So yeah, let us consider the coalescence time for two bubbles. Let us consider we have two bubbles B1 and B2. The coalescence time is let us say 2 seconds. Okay, actually I messed up the statement. If interaction time is greater than coalescence occurs. So if it is 2 seconds and interaction time is 3 seconds, then the bubble has interacted for quite a long time than what is required for coalescence. So we say that coalescence occurred. So it is both A and B, or either A and B. Option A and B is the right answer. Option D is the right answer. So the coalescence efficiency between two bubbles depends on coalescence time and interaction time. Interaction time is the time that taken by the bubble to be in contact with each other, whereas the interaction time is, coalescence time is the time taken for the bubbles to coalesce. So that is the difference. Now let us go to question 9. In question 9, based on the drainage model, the coalescence time is estimated as dash, where Tc, rho c, dB, sigma are coalescence time, density of continuous phase, bubble diameter and surface tension respectively. So based on the drainage model, the coalescence time is estimated as dash. In the option, we are asked to find Tc and given parameters are rho c, which is the density of continuous phase, and diameter of bubble, which is dB, and sigma surface tension respectively. Surface tension. So now we need to find Tc, and options given are option A, Tc is proportional to rho c to the power of 1 by 2, dB to the power of 3 by 2, sigma to the power of minus 1 by 2. Option B, Tc is proportional to rho c, that is density of continuous phase, to the power of 1 by 3, diameter of bubble to the power of 3 by 2, surface tension to the power of minus 1 by 2. Option C, coalescence time is proportional to density of continuous phase to the power of 1 by 2, diameter of bubble to the power of 3 by 2, and surface tension to the power of 1 by 2. And last option, it is Tc, that is continuous phase, coalescence time is proportional to density of continuous phase to the power of minus 1 by 2, diameter of bubble to the power of 3 by 2, and surface tension to the power of minus 1 by 2. So answer is actually Tc proportional to, that is coalescence time is proportional to rho c, that is density of continuous phase to the power of 1 by 2, and diameter of bubble dB to the power of 3 by 2, and sigma to the power of minus 1 by 2. Answer is option A. Option A is the right answer. So just remember that Tc is directly proportional to rho c to the power of 1 by 2 and inversely proportional to the power of inversely proportional to sigma to the power of 1 by 2. So it is rho c 1 by 2 sigma minus 1 by 2. Rho c 1 by 2 sigma minus 1 by 2. And in addition, we have one more parameter dB, diameter of bubble, so it is to the power of 3 by 2. So in all the options, if you look at, you have dv to the power of 3 by 2 is kept constant over here. So in this options, it is not confusing, but in exam the same question might be asked with different options. So please be careful of the coefficients and exponential terms in the equation. These questions might come in exam as well. So please be careful when you are choosing things. So that is question 9. Let us go to question 10. In question 10, it is given that higher coalescence efficiency obtained when option A small bubbles and low approach velocities, option B large bubbles and low approach velocity, and option C small bubbles and high approach velocities, and option D large bubbles and high approach velocities. So higher coalescence efficiency is obtained when dash. So it is basically option A small bubbles and large, small bubbles and low approach velocities. So at that time the coalescence efficiency is quite high. So when you have smaller bubbles and smaller approach velocities, the coalescence efficiency is high. So you can inversely relate these terms. Coalescence efficiency is inversely related to bubble size and approach velocities. So high coalescence efficiency, smaller bubbles and low approach velocities. But if you have large bubbles and large approach velocities, what will you have? You will have a low coalescence efficiency. So in that way you can remember things. So the question here is higher coalescence efficiency obtained when small bubbles and low approach velocities. Option A is the right answer. So we have rightly found out the answer. Now let us go to question 11. In question 11 it is asked that according to Quilaglo and Tavlerite's 1977 model, liquid droplet coalescence probability can be expressed as dash, where PC, TI and TC are coalescence probability, interaction time and coalescence time. So according to Quilaglo and Tavlerites, the liquid droplet coalescence probability can be expressed as dash liquid droplet coalescence probability. So that liquid droplet coalescence probability is PC. So we are asked to find the equation for PC, and in that equation what are the other terms? We have Ti and Tc. Ti is the interaction time and Tc is the coalescence time. Option A, actually this is an exponential equation. PC is equal to exponential of minus Tc by Ti, I guess. So first one, option A, PC is equal to exponent of minus Tc by Ti, where PC is the coalescence probability, Tc is the coalescence time and Ti is the interaction time. Option B, coalescence probability is equal to exponential function of Tc by Ti. Tc is again coalescence time, Ti is interaction time. Option C, PC is equal to exponential function of Ti by Tc. And last option, it is coalescence probability is equal to exponential of minus interaction time Ti divided by coalescence time Tc. So answer I guess is option A or D. Option A is the right answer, where PC, that is coalescence probability, is equal to exponential function of minus is there, be careful, and Tc, that is coalescence time, divided by Ti, that is interaction time. So PC is equal to exponential of minus Tc by Ti. So now let us go to question 11. Now we have seen 11, we will go to question 12. The coalescence time decreased with increasing volumetric concentration of particles. What about bubble coalescence with increasing volumetric concentration? Option A, bubble coalescence remains constant. Option B, bubble coalescence is enhanced. Option C, bubble coalescence is diminished. Option D, all of these. So let us now look at the question first carefully. In the question, the first statement given is that coalescence time decreased with increasing volumetric concentration of particles. So when you are increasing the volumetric concentration of particles inside the system, the coalescence time has decreased. What happens when you are increasing the volumetric concentration of the particles? What happens to the bubble coalescence? So here uh, the same condition is applicable. In both the cases you are increasing the volumetric concentration. So in the first one coalescence time has decreased. What happens if coalescence time is decreased? Bubble coalescence is enhanced because when the interaction time is constant and it should be more than coalescence time. So if coalescence time is decreased, you are obviously at advantage for it to have more coalescence. So in that case bubble coalescence is enhanced. Option B is the right answer. So why are you able to understand the thing happening? Why when you are just increasing the volumetric concentration of particles inside the system, and first case it because of the increase in the particles inside the system, the coalescence time has decreased, and because of the decrease in coalescence time, the coalescence is enhanced because the chances of coalescence is now increased. Why? Because coalescence time has decreased. The interaction time you can have, I mean, if it is constant also, like compared to previous case, the bubble coalescence is improved or is enhanced. So therefore option B is the right answer. Option B is the right answer. Now let us go to question 13. In approach stage of coalescence, which bubbles move faster? Option A, trailing bubble. Option B, leading bubble. Option C, both have same velocity. Option D, contacting bubble. So we say that in vertical direction, a bubble approaches the trailing bubble, that is, let us consider two bubbles. This is leading bubble. Leading bubble. And this is trailing bubble. So, I mean, this is inside the fluidized bed. We are passing air and solids will be there. So, now in approach stage, what happens is that the trailing bubble uh, moves faster, trying to collide with the leading bubble. So it tries to catch up with the leading bubble. So that is what happens in the approach stage of coalescence. The trailing bubble tries to catch up with the leading bubble so that they can coalesce. So it mainly things to be noted is the question is regarding where it is approach stage of coalescence, which bubble move faster. It is not in coalescence stage, so please keep that in mind. It is asked in approach stage of coalescence, which bubble moves faster. So option A, trailing bubble. Option B, leading bubble. Option C, both have same velocity. Option D, contacting bubble. So option A is the right answer, trailing bubble. Because in approach stage, trailing bubble moves faster trying to catch up with the leading bubble. So option A, trailing bubble is the right answer. So let us look at the option. Answer. Answer is option A, trailing bubble. So that is what is question 13. Let us go to question 14. At the coalescence stage, before the liquid film ruptures, the distance between the contacting bubbles dash. At the coalescence stage, before the liquid film ruptures, the trailing bubble, the distance between the contacting bubbles dash. Option A, half of the film thickness. Option B, remains constant. Option C, decreases. Option D, increases. At the coalescence stage, before the film ruptures, the distance between contacting bubble remains constant. Like previously the question was about approach stage. Now the question is about coalescence stage. So the bubbles are now at coalescence stage, and before they have collided, and they, as we have seen, the bubbles collide and the surface of the bubbles which have collided become flattened, and then the liquid film becomes entrapped inside, and therefore after that the before the liquid film ruptures, the distance between the contacting bubble remains same. So at the coalescence stage, there is no need for the bubble to catch up or do something, so it remains constant. So at the coalescence stage, the distance between the bubbles remains constant, whereas in the approaching stage, like in last question, at approaching stage, the trailing bubble goes with faster velocity trying to catch up with the leading bubble. Therefore, their distance reduces. But in coalescence stage, that is why I underlined the previous question also. At the coalescence stage, before the film ruptures, distance remains constant. Distance between the contacting bubble remains constant. So answer is option B is the right answer. Question 14, option B. Now let us go to question 15. In an air-water system, the instability of an interface is due to dash. Option A, variations in velocity and density. Option B, variation in density and surface tension. Option B, only variation in viscosity. Option D, all of these. So here the instability of an interface is due to dash in an air-water system. So one thing is like velocity with which they move. So velocity is an answer, and also distance between, density between, difference between the fluid, that is water and air, is also an issue causing an instability in the interface. So answer is option A. Density plays a role, as we can see from option A and B. So density is an important parameter, and also the velocity with which they move is also important. So velocity and density, but surface tension and viscosity doesn't play any role. So we are saying that the instability of an interface is due to variation in velocity and variation in density. Option A is the right answer. Now let us go to question 16. In question 16 it is asked that in turbulent multiphase flow, a common phenomenon that causes bubble breakup is. So what are we asked? In turbulent multiphase flow, a common phenomenon that causes bubble breakup. Till now we have seen about bubble coalescence. Now the question is about bubble breakup, and that too in a turbulent multiphase flow system. So what is the common phenomena that is causing bubble breakup? Option A, coalescence in axial direction. Option B, coalescence in radial direction. Option C, variation of pressure along surface of a bubble. Option D, turbulent motion. So we are given that four options. Coalescence in axial direction, it happens, but it doesn't have much to do with bubble breakup. So this is wrong. And similarly, coalescence in radial direction doesn't have much to do. Whereas variation of pressure along the surface of a bubble is an important factor which causes bubble breakup. So option C is the right answer, and turbulent motion again doesn't have anything to do with this. So answer is option C. In a turbulent multiphase flow, a common phenomenon that causes bubble breakup is variation of pressure along the surface of a bubble. Option C is the right answer. Now let us go to question 17. Higher eddies result in more dash. Option A, bubbles are diminished. Option B, bubbles are transported. Option C, bubbles lose their mass. All of these. So thing is, like, if eddies are same size as bubbles, they are like diminished, like they are resulting in bubble breakups. If eddies are of same size as the bubbles, if eddies are of the same size as bubbles, bubbles are diminished. But in this particular question, what is asked? We are asked about higher eddies, that is larger eddies. If eddies are larger than bubble size, what happens is that bubbles are transported. Bubbles are transported. This happens when eddies are same size. Or of same size as bubbles. But transported, where is my cursor? Eddies larger than bubbles. So answer is option B. Bubbles are transported. Now let us go to question 18. Okay. Question 18. Bubbles. Critical information required for universal bubble breakup model is dash. Breakup of parent bubble, daughter bubble size. Option C, both A and B. Option D, coalescence. So when you are studying with the universal bubble breakup model, what critical information do you require? First one, it is that you require information pertaining the parent bubble, like breakup of the parent bubble, but that information is required. And second one is daughter bubble size. So we are saying that parent bubble gets broken and daughter bubbles form. So what is the critical information required? We require information about the breakup of the parent bubble and also the information about the daughter bubble size. So what is the size of the daughter bubble it has formed is also very much important. So answer to this question is actually option C. Both A and B is the right answer. So now let us go to question 19. Option C, both A and B is the right answer. We require information about the breakup of parent bubble. We also require information about the daughter bubble size. So both A and B is the right answer. Now let us go to question 19. question 19, it is asked that the breakup efficiency of the bubbles is 0 when dash. So breakup efficiency of bubble is 0 when dash is the question. So in this we need to identify some relation at which the breakup efficiency of bubble is 0. So in the parameters in the equation are d, which is bubble diameter, and d max, which is maximum bubble diameter. So breakup efficiency of the bubbles is 0. Can you guess actually? It is very simple actually. Here d is diameter of the bubble and d by x is maximum diameter of the bubble. So when does bubble breakup occur? Mostly when it reaches the bubble maximum bubble size, and then it disrupts it and leading to smaller bubble formation. So when d is less than d max, bubble breakup would not be happening in most cases. So breakup efficiency of the bubble is therefore 0. So you can say the answer without option itself when you think logically. So answer is d less than d max. So let us just go and look at the options once again. D less than or equal to d max, option A. Option B, d equal to d max. Option C, d greater than or equal to d max. Option D, d is 0.5 d max. So here the question is about breakup efficiency of the bubble is 0 when d and d max relation is dash. So option A, d greater than less than or equal to d max is what happens. So this is bubbles, and they need to, if d is less than d max, need to grow before breakup. So answer option A, d less than or equal to d max is the answer, and option B and C and D are wrong. B, C, D are wrong. Option A is the answer. Now if we look at question 20, in question 20, according to Levitch model, 1962 model, the maximum according to Levitch 1962 model, maximum stable bubble diameter can be calculated by dash, where d max is maximum stable bubble size, and sigma is surface tension, and rho L is liquid density, and rho G is the gas density, and UB is bubble rise velocity. So according to Levitch model, what is the maximum stable bubble diameter that can be calculated? I mean maximum stable bubble size that can be according to Levitch 1962 model, what is the maximum stable bubble diameter and what is the equation to calculate that? So we are asked to find d max equation. So d max is equal to dash. D max is equal to dash. In the equation, the terms are sigma, rho L, rho G and UB. Sigma is surface tension, rho L and rho G are density of liquid and gas, and UB is the bubble rise velocity. So answer is option. Let us look at the options first. Option A, d max is equal to 3.63 sigma divided by UB square into rho L square rho G power of 1 by 3. Option B, d max is equal to 3.63 sigma divided by UB square into rho G square rho L power of 1 by 3. Option C, 3.63 sigma divided by UB square into rho L square rho G to the power of 1 by 2. Option D, 3.63 into sigma into UB square into 1 by 3 to the power of, rho L rho G to the power of 1 by 3. I think it is D. Okay, Okay, yeah. Option A is the right answer. I'm sorry, I did wrong thing over here. So answer is option A. We are asked to find the maximum stable bubble diameter, and the formula to calculate that is D max is equal to 3.63 sigma divided by UB square into rho L square into rho G to the power of 1 by 3. D max is the maximum stable bubble diameter, and 3.63 into sigma. Sigma is the surface tension, and UB is the bubble rise velocity. Rho L is the density of liquid. Rho G is the density of gas to the power of 1 by 3. So here 3.63 is some parameter. Sigma is the surface tension which remains the same. UB square also remains the same. And rho L square, rho G to the power of 1 by 3 is what is varying in all these four terms. So how we should remember that? How are we going to remember? So it is according to Levitch 1962 model, and we are asked to find the maximum stable bubble diameter. So remember that where Levitch has L. So it rho L, rho G has one more additional L. So rho L square. So the square comes in rho L term. Rho L square into rho G, and to the power of 1 by 3. So 1 by 3 you can almost remember, but it should be rho L square into rho G. So that is the answer. So answer is option A, D max is equal to 3.63 sigma divided by UB square into rho L square rho G to the power of 1 by 3, where sigma is the surface tension, UB is the bubble rise velocity, and rho L is the liquid density, and rho G is the gas density. So I hope you are clear now. So this is few questions. Now we have questions from week 6 assignment problems, which will be just to revision. So let us take a 5 minutes break and then come back. So the time now is 3:58. So let us go break and we'll come back. Okay. Okay, so now let us start again. So this is week 6 assignment problem. So just let us quickly go through these problems as well. Okay. So the question one is, thumb rule for pressure drop across distributor is dash, where delta PD and delta PB are pressure drop across distributor and pressure drop across bed. So delta PD is equal to 0.2 to 0.7 delta PB. Option B, delta PD is equal to 0.2 to 0.4 delta PB. Option C, delta PD is equal to 0.5 to 1 delta PB. And option D, it is delta PD is equal to 1 to 2 times of delta PB. So delta PD is pressure drop across distributor and delta PB is pressure drop across bed. So it is how much percentage of pressure drop across the bed should distributor be coming from. So if imagine if it is 1 to 2 times of delta PB, it would not work at all. Similarly, this if it is this high and this high, it would again not work. So answer is actually 0.2 to 0.4 times of delta PB. Delta PD, that is pressure drop across distributor, is equal to 0.2 to zero point 0.4 times of delta PB. Here delta PB means pressure drop across bed and delta PD means pressure drop across distributor. So option B is the right answer. Now let us go to question 2. At a very low gas flow rate, the frequency and sizes of bubbles formed are primarily governed by dash. Option A, surface tension of liquid. Option B, buoyancy force of the bubble. Option C, both A and B. Option D, none of the above. So answer is actually both A and B is the right answer because it is governed by surface tension of the liquid and buoyancy force of the bubble. So the right answer to this question is option C, both A and B. And now let us go to question 3. In question 3, bubble formation in a fluidized bed is very similar to that in dash. Option A, an inviscid liquid. Option B, a viscous liquid. Option C, a boiling liquid. Option D, all the above. So bubble formation in a fluidized bed is very similar to that in an inviscid liquid is the right answer. So all these things you have seen in last class itself. So I am going a little bit fast. If at any point of time you want me to stop or reduce my speed, please let me know. Since we know these concepts already, I am going a little fast. That's it. And the first one, bubble formation in a fluidized bed is very similar to that in an inviscid liquid is the right answer. So answer to this question is option A. So now question 4. In question 4, above the critical Froude number, option A, jets are present in the fluidized bed. Option B, bubbles are found in a fluidized bed. Option C, both A and B. Option D, none of the above. I guess above the critical Froude number, bubbles are found inside the fluidized bed. So option B is the right answer. And if we look at the explanation for why, so remember the question is about above the critical Froude's number. What happens? Bubbles are found in a fluidized bed. So Froude's number was derived from experiments with model boats a few meters long. So Froude's number, as we all know, is a dimensionless number. So what is the importance of Froude's number? It is that for deriving Froude's number, it was derived using experiments conducted using model boats, and the number expresses the characteristics of flow. including surface waves and bed forms as a ratio between the gravitational force and inertial forces. So Froude's number is the ratio between the gravitational force and inertial forces. So the number, that is the Froude's number, expresses the characteristics of flow including the surface waves and bed forms. Including the surface waves and the bed forms, and therefore from the Froude's number we can see what is the characteristics of flow that is happening inside the system. And option Froude's number Froude number Fr is equal to V by square root of G into D, and in this expression V is the bulk flow velocity, G is the gravitational constant, D is the water depth. So what they have done experiments using a model boards and derived the expression for Froude's number, which is V by square root of G into D. V is the bulk flow velocity, G is the gravitational constant, D is the water depth. And from this number they were able to say the characteristics of fluid flow including the surface waves and bed forms. So now when Froude's number is equal to 1, then any surface will remain stationary. If Froude's number is less than 1, inertial forces were dominating and it resulted in subcritical flow conditions. Tranquil flow. This corresponds to lower flow regime bed forms such as ripples and large dune structures. And if Froude's number is greater than 1, gravitational forces dominate, resulting in supercritical flow conditions. These force domination alone, I'm not sure, but it is in supercritical flow conditions, and corresponding stream flow surface conditions manifest as an acceleration of flow that such stationary waves break upstreams, huge upper flow regimes. So the moral is that we can actually remove all these things. So if it is above critical flow conditions, V is said to be high, and if velocity is high, we say bubble formation occurs. So therefore, if Froude's number is greater than critical Froude's number, bubble formation tends to occur inside the fluidized beds. That is this question. Now let us go to question 5. The ratio of specific heat of gas is dash, where CPG and CVG are specific heat capacity of gas at constant pressure and constant volume. The ratio of specific heat of gas is dash, and ratio of specific heat of gas is given by gamma. Gamma is equal to, we all know it as Cp by Cv, and in that formula Cpg is the specific heat capacity of gas at constant pressure and Cvg is the specific heat capacity of gas at constant volume. Even though we know the answer, let us once look at the options. Option A Cpg by Cvg, option B Ctg by Cvg, option C Cpg by Cv, option D Cg by Cvg. So the right answer to this particular question is option A, that is Cpg by Cvg. I hope it is clear now. We'll go to question 6. In case of a stern bubbles in a vertical tube generated continuously by blowing air in at the bottom, the peak velocity at the middle of the tube is about dash. In case of a stream of bubbles in a vertical tube generated continuously by blowing air in at the bottom, the peak velocity at the middle of the tube is about dash. 0.5 times average velocity, 1.2 times the average velocity, equal to the average velocity, option D, none of the above. So when we are passing or we are generating bubbles inside the vertical tube, By continuously blowing air at the bottom, the peak velocity in the middle of the tube is actually about 1.2 times the average velocity. So answer is option B. So let us go to question 7. Just give me a minute. So now question 7. The bubble velocity is affected by the presence of vessel wall when bubbles are large enough to exceed approximately dash. So all these things we have seen in the last class itself. So I hope it was helpful for you guys in solving the assignments. So on that basis, now let us look at the options. Option E, it is 25% of column diameter. Option B, 15% of column diameter. Option C, 10% of column diameter. Option D, all the above. So what is the question? The question is that the bubble velocity is affected by the presence of the vessel wall when bubbles are large enough to exceed approximately dash. So if 25% of column diameter is the right answer, option A, we say that when bubble size are certainly larger than something, then wall effects comes into picture. That is what we have seen in the last class. So when does that happen? When the bubble size is larger than 25% of the column diameter. If it is larger, then wall effects comes into picture. Option A is the right answer. Question 8. The wall effect becomes negligible only when equivalent bubble diameter is dash. Less than zero point 0.1 of the bed diameter, more than zero point 0.1 of the bed diameter, equal to the bed diameter, all the above. So we were saying if bubble diameter is larger than 0.25 times bed diameter, it was coming into picture and it was giving a very large impact. But when can we neglect the effect of bubbles? When the bubble equivalent diameter is less than 1.1 of the bed diameter is the right answer. That is, if it is less than 10% of the bed diameter, we can say that bubble um, has no impact from the walls, column walls, that is, it has no impact. So option A, less than zero point 0.1 of the bed diameter is the right answer. Now let us go to question 9. In question 9 it is asked that for fine particles minimum bubbling velocity is dash. Option A, equal to minimum fluidization velocity. Option B, larger than minimum fluidization velocity. Option C, smaller than minimum fluidization velocity. Option D, all the above. So in this particular question we are asked for finer size particles what happens or what is the relation between the bubbling velocity or minimum bubbling velocity and minimum fluidizing velocity. Minimum fluidizing velocity is the velocity at which the bed packs in the loosest state, and we can say that once the velocity is exceeded, the pressure drop remains the constant and the solid starts to move. At minimum fluidization condition, the packed bed is not as tightly packed as it remains in the packed bed conditions, but it is the particles are not moving too. That is what we call as minimum fluidization condition or incipient fluidization also. So the velocity at the minimum fluidization velocity is the UMF, that is minimum fluidization velocity. Minimum bubbling velocity is the velocity at which bubbles start to form inside the bed. So it depends on the depending on the particle size, the bubbling regime might coincide with fluidizing regime or might occur at a later stage than the fluidizing condition. So when finer size particles, what is the relation between minimum bubbling velocity and minimum fluidization velocity? It is larger than minimum fluidization velocity. Option B is the right answer. For finer size particles, the first minimum fluidization condition occurs, and at later stage after some time minimum that is the bubbling fluidization occurs, and it is UMB. So UMF is larger than I mean UMB is larger than UMF. UMB, that is minimum bubbling velocity, is larger than minimum fluidization velocity, or in other words minimum fluidization velocity is smaller than minimum bubbling velocity. We can say in both the terms. Alright. In between, smooth fluidization might occur. That is what we might mean by this statement. So that is question 9. Now let us go to question 10. So now let us go to question 10. The bubbles in fluidized beds grow in size due primarily to the factor or factors. So the bubbles in fluidized beds grow in size due primarily to the factors. Option A. Effective hydrostatic pressure decreases towards the top of the fluidized beds. Option B. Bubbles coalesce in vertical direction with the trailing bubble catching up with the leading bubble. Option C. Bubbles coalesce in horizontal direction with the neighboring bubbles. Option D. All the above. Can anyone answer this? Answer is all the above. Bubbles in fluidized beds grow in size. When does bubbles grow in size? When they coalesce or something happens inside the system. So effective hydrostatic pressure decreases towards the top of the bed. So that time bubbles can grow in size. And because of bubble coalescence in horizontal and vertical directions, also bubbles can grow in size. Bubbles coalesce in vertical direction when the trailing bubble catches up with the leading bubble, as we have seen in today's class. And also bubbles coalesce in size in the horizontal direction with the neighboring direction, with the neighboring bubbles. So all the above is the right answer. Now let us go to question 11. In question 11 it is asked that the fluidization behavior of the powders was independent of both of the mean particle size and of the particle size distribution for group A powders, option B group B powders, option C group C powders, option D all the above. So fluidization behavior of powders was independent of both mean particle size and particle size distribution for. So for finer size particles we have seen that it is dependent on particle size. The fluidization behavior is dependent on particle size. So mostly A and C comes under fines. So in that aspect, if we think in regards to that, we can say that the answer is option B, that is group B powders is the right answer. Group B powders is the right answer. Now let us go to question 12. Mean bubble size in a fluidized bed is found to be dependent on dash. Mean bubble size in a fluidized bed is found to be dependent on dash. Option A, type of the distributor. Option B, distance above the distributor plate. Option C, excess gas velocity above that required at the minimum fluidization condition. All the above. So bubbles form inside the fluidized beds. And what are all the factors influence the size of the bubbles? Does type of distributor influence? Actually answer is all the above. So does the type of distributor influence the size of the bubbles? As like for different type of distributors we have porous type distributor, perforated plates distributor, Dios type distributor. So type of distributor plays a role in formation of bubbles. Second one, distance above the distributor plate. Again, like bubble size varies at different heights. So distance above the distributor plate is also a factor. And last one, excess gas velocity above that required at minimum fluidization condition. So what we call as bubbling fluidization, when we pass a fluid at a sufficiently higher velocity than the minimum fluidization velocity, bubbles tend to form inside the fluidized bed. So that excess gas velocity is required to form bubbles. So option C, excess gas velocity required, velocity above that required at the minimum fluidization condition is also the answer. So answer is all the above. Now let us go to question 13. In question 13, according to Mori and Win's 1975 model, maximum bubble size depends on dash. Option A, relative velocity of the gas to the minimum fluidization condition. Option B, cross-sectional area of the bed. Option C, both A and B. Option D, none of the above. So I would like to mention that Mori and Win is 1975 model is a very famous model which helps us to know the maximum bubble size. So it in fact depends on relative velocity of the gas to the minimum bubbling velocity, minimum fluidization velocity. Obviously the excess velocity is what leads to formation of bubbles, and cross-sectional area of the column also is a factor. dB max, actually I don't remember the formula, but it somehow relates all these parameters, yeah, and put in the equation that deals with includes all these terms in the final equation, where in Mori and Win's 1975 model the maximum bubble size depends on cross-sectional area of the bed and relative velocity of the gas to the minimum fluidization velocity. So answer is option A and B. Now let us go and look at question 14. We have 5 more questions. For a porous plate distributed, the value of H naught, which is the characteristics of distributed plate, should be equal to dash. So it is for a porous plate distributor, the value of H naught. H naught is some empirical parameter in the equation, and it is the characteristics of distributed plate should be equal to dash. Option A, H naught is equal to 0.5. Option B, H naught is equal to 1. Option C, H naught is equal to 1.5. Option D, H naught is equal to 0. And option D, H naught is equal to 0 is the right answer. Uh, if it is a perforated plate distributor, H naught is greater than 1 meters, I think. Please just make sure. But for porous plate distributor, this empirical constant in the equation is 0. The value of H naught, which is the characteristics of distributed plate, is equal to 0. I think it is somehow related to the bubble size formation inside the bed, but H naught is an empirical constant and it is 0 for porous plate distributor, and I think it is greater than 1 for perforated plate distributor. That is question 14. Question 15 is catchment area of distributed plate is defined as dash. Option A, area of the distributed plate per hole. Option B, total area of distributed plate. Option C, half area of the distributed plate. Option D, all the above. Catchment area of the distributed plate is nothing but area of the distributed plate per hole is the right answer. The catchment area of a distributed plate is defined as the area of the distributed plate per hole. So that is what we call as catchment area of a distributor. So answer is option A is the right answer. Area of the distributed plate per hole. Catchment area of a distributed plate is defined as dash. Option A, area of the distributed plate per hole. Option B, total area of the distributed plate. Option C, total half area of the distributed plate. Option D, all the above. The right answer is area of the distributed plate per hole. Option A is the right answer. Now let us go to question 16. In question 16, it is asked that if the bubbles grow to the size of the vessel diameter, the bed becomes dash. Option A, a bubbling bed. Option B, a slugging bed. Option C, a stratified bed. Option D, none of the above. I guess we all know the answer to this question at this point because we have seen this particular question in all forms since last week. So, if bubbles grow to the size of the column, size of the vessel diameter, bubbles become slugging bed. So, in slugging bed only we have seen that the bubbles will grow in size and reach to the size of the column and they almost occupy the size of the column. That is what we call as slugs, and we have flat slugs and two slugs are there. Uh, axial slugs and flat slugs. In axial slugs, the bubble size is growing, and in flat slugs, it almost reaches the size of the bubble column. So we have two types of slugs, axial slugs and flat slugs. In axial slugs, these slugs or these bubbles grow in size, and in flat slug, they almost reach the size of the column. That is what we call as flat slugs. If a bubble grows to the size of the vessel diameter, the bed then becomes a slugging bed. So the right answer to this particular question is option B is the right answer, a slugging bed. Now let us go to question, I guess question 17. The coalescence frequency per unit volume FCV inside a fluidized bed is proportional to dash. The coalescing frequency per unit volume FCV. The coalescing frequency per unit volume. So FCV, coalescing frequency per unit volume, is inside a fluidized bed is proportional to dash. Option A, diameter of the spherical bubble. Option B, square of the diameter of the spherical bubble. Option C, cube of the diameter of the spherical bubble. Option D, none of the above. So answer is actually square of the diameter of the spherical bubble. So we have seen this in the last class itself, how it is. So bubble coalescence frequency, that is per unit volume FCV, is equal to 0.5658 into pi into VB dV square n square. So from this we have solved one problem in last class also. I don't know if you guys remember that, but the frequency of coalescence frequency per unit volume is proportional to square of the diameter of the spherical bubble. FCB is proportional to square of the diameter of the spherical bubble. Option B is the right answer. So how is the formula for coalescence frequency per unit volume inside a fluidized bed? FCV is equal to 0.5658 into pi into VB into dB square into n square. This dB has square, so it is square of the diameter of the spherical bubble. So answer is option B. Now let us go to question 18. In question 18, it is asked that for coarse particle, the minimum bubbling velocity is dash, equal to minimum fluidization velocity, larger than minimum fluidization velocity, smaller than minimum fluidization velocity, all the above. So for finite size particles, we have seen that the minimum bubbling velocity is larger than minimum fluidization velocity. So how is it related to coarser size particles? I guess it is equal to minimum fluidization velocity. Option A is the right answer. How? For finer size particles, the UMP is greater than UMF. So bubbling occurs after some stages of minimum fluidization. Whereas when we are dealing with coarser size particles, bubbles start producing at immediately after fluidization. So that is why the minimum bubbling velocity is equal to the minimum fluidization velocity. For finer size particles, if you remember, the minimum bubbling velocity was greater than minimum fluidization velocity. So after fluidization, the smooth fluidization or homogeneous fluidization might occur, after which the bubbles might start producing. But in coarser size particles, if For example, if you remember Gelda D particles, it is mostly used in spouted fluidized beds. There will be vigorous formation of bubbles when we are dealing with Gelda D particles. Gelda D are coarser size particles, that is larger size particles. So when we are dealing with coarser size particles like Gelda D, their minimum bubbling velocity is equal to the minimum fluidization velocity. Are you getting my point? Their minimum bubbling velocity is equal to the minimum fluidization velocity. So bubbles start forming immediately after the fluidization. So option A is the right answer. Let us go to last question for today's session. Question 19. Equilibrium bubble diameter dash. Equilibrium bubble diameter. Option A decreases linearly with the ratio of volumetric bubble flux to the splitting frequency of a bubble. Option B increase linearly with the ratio of volumetric bubble flux to the splitting frequency of bubble. Option C remains constant with the ratio of volumetric bubble flux to the splitting frequency of a bubble. Option D none of the above. Uh, the question is about what happens to the equilibrium bubble diameter in relation to the ratio of volumetric bubble flux to the splitting frequency of a bubble. Now I guess it is produced per unit area. So answer is option B. Increases linearly with the ratio of volumetric bubble flux to the splitting frequency of a bubble. So what happens is that when we are dealing with equilibrium bubble diameter, uh, when volumetric bubble flux to the ratio of splitting frequency increases, the equilibrium bubble diameter also increases. So we say that equilibrium bubble diameter increases linearly with ratio of volumetric bubble flux to the splitting frequency of a bubble. Volumetric bubble flux meaning volumetric production of bubbles per unit area per unit second. So if bubble size is increased, so bubble diameter is therefore linearly increasing with the ratio of volumetric bubble flux to the splitting frequency of a bubble. Option B is the right answer. So that is for question 19. So that is all for today's class. So what we have seen in today's class, we have seen mostly about bubble coalescence. So when does bubbles coalesce? They can coalesce in horizontal or vertical direction. In horizontal direction when they collide with the neighboring bubbles, or in vertical direction when the trailing bubble reaches the or catches up with the leading bubble. So the trailing bubble moves faster and catch up with the leading bubble, and therefore they collide and coalesce. How does bubble coalesce? When two bubbles collide with each other, their surface flatten and they entrap the liquid between them, and then they collide. They coalesce. So, what are the chances for three or more bubbles colliding? It is very, very low, because normally we consider the collision of two bubbles at a time. At that time, that is important. At the single instant, we mostly consider the coalescence of two single bubbles. So, that is one thing. And what are all the different concepts we have seen in today's class? So, collision. Random bubbles, we have seen collision frequency is directly proportional to the diameter of the bubble. and also bubble rise velocity is proportional to the size of the bubbles. Therefore, larger bubble has larger rise velocity. And wake layer and Mu's model bubble coalescence occur when a bubble enters another bubble's wake, and wake affect inline coalescence. And Hibiki and Ishii results due to wake induced entrainment and turbulent induced entrainment as well. And coalescence depends on coalescence time and interaction time. When interaction time is larger than coalescence time, the bubble coalesce. And when volumetric concentration inside the of particles inside the system is more, that results in reduced coalescence time. So therefore bubble coalescence is enhanced. So this is one formula we have seen. Tc is directly proportional to rho c 1 by 2 dB power 3 by 2 sigma power minus 1 by 2. And higher coalescence efficiency obtained when small bubbles and low approach velocities. So and Tc is equal to exponential of minus Tc by Ti. Tc is the coalescence time and Ti is the interaction time. So these are the concepts we have seen, like this is what I have mentioned. When coalescence time decreases with increasing volumetric concentration of particles, what about bubble coalescence with increasing volumetric concentration? Bubble coalescence is enhanced. And approach stage, trailing bubble moves faster and it reaches the leading bubble, whereas in coalescence stage the distance between the bubble remains constant. The distance between the contacting bubble remains constant. So what stage is important? At approaching stage, the distance between the trailing bubble and reducing bubble diminishes because the trailing bubble reaches the leading bubble faster. Whereas in coalescence stage, the distance between the contacting bubble remains a constant. And what are the concepts? In air water system, instability is due to velocity and density variations. And turbulent multiphase flow, a common phenomena causes bubble breakup is a variation of pressure along surface of a bubble. And higher eddies results in more bubbles being transported, whereas bubbles of same size as the eddies results in bubbles being diminished because of the eddies. Whereas higher eddies results in more bubbles being transported. And these are the concepts. Critical information required for bubble breakup is breakup of parent bubble and daughter bubble size. So bubble coalescence and bubble breakup is what was covered in this week's lectures. So we have seen problems from that and we have covered few concepts related to that. And if D is less than D max, the breakup efficiency is 0 because D max is the maximum stable bubble diameter. Below that, the chance for the breakup of the bubbles is low or 0. So breakup efficiency is 0. So that is this week's problem. According to Levitch, I have seen rho L square because we are using Levitch L, rho L square, rho G 3.63 sigma by UB square into rho L square into rho G power of 1 by 3. What is this formula is for? It is for calculating the maximum stable bubble size. So this is the problems we have dealt with in today's class regarding week 7. And week 6 problems also we have seen pressure drop, distributor and bubble formation. So I guess these problems are a bit repetitive, so you might be very much clear in these problems. So I'll leave you to that. If you have any doubts in today's class, please feel free to ask now. We have 5 more minutes. Time now is 4:48. I'll wait for 5 more minutes, and if there are any doubts, we can clarify now, or else we can close the session. So if there are any doubts, let me know. Hello, hello. Okay, I guess it is. Since there are no questions, I'm going to close the session. And thanks everyone for attending. We will have next session by next week. And yeah, we'll have the session at the same time.